Hello, welcome to second lecture of module 3. This is lecture number 23 of the course. In this lecture, initially we'll discuss the very important parameter called quality factor of every cavity. Then we'll try to guess the Hamiltonian of a typical cavity optomechanical system based on reasoning. Then we'll start discussing the basic physics of a cavity optomechanical system, assuming the radiation pressure force to be an instantaneous function of the movable mirror. So let us begin. In the last class, we started discussing cavity optomechanics. A typical cavity optomechanical system consists of two mirrors, where one of the mirror is fixed and the other mirror is movable, or we can consider it as a mechanical oscillator. And the main idea in cavity optomechanics is to make light interact with the mechanical system or the mechanical oscillator in a controlled way via the so-called radiation pressure force. And as I said, the two articles that we are going to rely in our discussion is one by Marcus Espelmeyer, Tobias Kippenberg, and Florian Marquardt, that is KBT Optomechanics, and another one, this article by Pierre Mester, called A Short Walk Through Quantum Optomechanics. So cavity optomechanics, which is also shortly called quantum optomechanics, more popularly nowadays it's known like that, is an emerging area in physics and which utilizes quantum optics tools in condensed matter system. And these systems are typically cantilevers, beams, and these are oscillators. These oscillators vibrate in the frequency range of kilohertz to gigahertz, and there are varieties of system. In fact, a plethora of such systems are available, which I pointed out in the last class. And the sizes in terms of the masses, they can be from 1 gram to very small mass, very tiny mass, even in the range of zeptogram, that is say 10 to the power minus 21 gram is 1 zeptogram. Interestingly, the same physics over these 20 orders of magnitude is applicable. And what is striking is that all these models, different looking or systems or optomechanical devices, can be modeled by this simple model where we have one fixed mirror and another one is the movable mirror. And we'll see in today's class how we can actually model it. A typical Hamiltonian we can write for this particular cavity optomechanical system, and this Hamiltonian would contain all the necessary physics. And goals of cavity optomechanics are twofold. Firstly, to probe not necessarily firstly, one of the goal is to probe fundamental physics and to exploit these concepts for various applications, primarily in the so-called quantum technologies. And one of the very ambitious goal is to push the so-called classical and quantum boundary. And the idea is to whether we can push this quantum boundary towards the higher. That means whether we can apply quantum mechanics to massive objects like this. And that is one of the very ambitious goal. In principle, yes, we can do that. And in this regard, the so-called Schrödinger cat problem, that has a mechanical analog where we have this cantilever, and we can create a situation where this cantilever may be in a superposition of two states. One location is denoted by K0 and another one is K1. This kind of superposition state can be created in the laboratory, and this way we'll be able to test quantum mechanics in an entirely new domain. And also it is possible to produce non-classical states of heavy mechanical objects and test quantum mechanics. One main advantage of this mechanical system is that they can be coupled to various quantum systems and they can act as a transducer, as I explained in the last class. and this is a very important, actually very useful, as we'll see later on. To just give an example or to remind you, for example, we cannot directly transfer our information that is stored in a superconducting qubit or a circuit to a optical fiber, because we cannot couple it directly to light. What we can, however, do is that we can couple the superconducting circuit or that qubit to a mechanical system, and that mechanical system then can be coupled to optical fiber, and that optical fiber will carry away the information. Okay, now there are various applications we talked about. One is to so-called quantum information processing, then ultra sensitive detection of very tiny forces, ultra sensitive detection of masses, and detection of very sensitive detection of displacement. And the best thing is that everything can be integrated on a chip, and nano fabrication techniques are already available. So solid state system in particular is mostly studied in this regard. The main mechanism behind this interaction between light and mechanics is the so-called radiation pressure force, and we discussed about it. It was primarily due to Arthur Eskin, who started this area, and he studied these things in great detail. It's very easy to understand. Say a photon is getting incident, and then with momentum h cross k, then if it is reflected from a perfectly reflecting mirror, the momentum that after reflection would be minus h cross for the photon. Therefore change in momentum would be twice h cross k, and this way we can find out the force if we have a stream of n number of photons, and that relation, the force would be 2 into power divided by c. And we analyze it little bit in details. If we just have a one mechanical oscillator or a vibrating mirror like this, then it turns out that when a photon is interacting with it, the displacement of the mirror is actually very small. In fact, it is far smaller than even the so-called 0 point fluctuation. So therefore it is impossible to observe quantum effects. In order to observe quantum effects, the displacement of this mirror has to be greater than the fluctuation due to the, or displacement due to the vacuum fluctuation, and that can, we from our analysis we see that can be possible if we put another mirror. That means we make it a cavity, and this is the reason why this cavity system is so popular and so effective. Okay, and as I said already, the generic model of a optomechanical system is represented by this diagram here, as it is shown. We have a fixed mirror here, and another mirror is movable, and this movable mirror, because this is a vibrating oscillator, so we can consider this vibrating oscillator has some mass m, and oscillation frequency omega m, and the phonon quanta of vibration is phonon. The phonon may decay at the rate gamma m. On the other hand, the cavity is this is characterized by the cavity resonance frequency omega c, and the cavity decay, photon decay rate, that is kappa, and a laser is getting incident on the on this mirror, and that has a wavelength lambda and frequency, angular frequency omega l, and power p. So the purpose of the cavity is to boost the light field interaction, this is already I said that one of the mirror is fully reflecting. For example, this one is fully reflecting while the other one is partially reflecting, so that we can get transmitted beam from inside of the cavity, and that transmitted beam, if we make measurement, that is going to tell us a lot of things what is going on inside the cavity. Okay, as you see that the Fabry-Perot cavity is basically the backbone of the whole system, so therefore we discuss Fabry-Pérot cavity in somewhat details, and we talked about the cavity resonance condition. This cavity resonance condition can be written in various form. So what does it basically means? That if light is to enter into the cavity, then this resonance condition has to be satisfied. Those light has this wave vector like this, or wavelength satisfy this condition, or frequency or the angular frequency, that light will be able to enter into the cavity, and will have a various peaks, and these peaks would be separated in frequency, and this separation is known as free spectral range. This is a very important quantity, and that is given by C by 2L. And then we went on to work out the intensity inside the cavity, and we found out this expression there. From here we can also find out that this resonance peaks has some width. These are called known as the full width at half maximum, and or it is also called the bandwidth, and we calculated it. All right, and then we finally, in the last class, we discussed about photon lifetime inside the cavity, because photon would not stay inside the cavity for eternity. After some time it will leak away, and there is a certain lifetime of the photon inside the cavity. And we went on to work it out, assuming that the survival probability of the photon is very high, because generally these mirrors are very high quality mirrors. So because there'd be very few losses, or the reflectivity is around 98 to 99%. So survival probability of the photon is pretty large. So under that approximation, then we went on to work out the photon lifetime, and we worked out a interesting relation, and this relation is called the cavity uncertainty relation, where this is basically the product of the cavity lifetime and the bandwidth is equal to 1 by 2 pi. So this is an important relation. It tells about, depending on the bandwidth, this basically means that if the bandwidth is very small, full width of the half maximum, then the photon lifetime would be larger. So that means if you have a very sharp peak, then from that we can say that the photon will be able to survive inside the cavity for longer amount of time. Now we are going to discuss a very important quantity, that is the so-called quality factor. I think all of you know how quality factor of an oscillator is defined. It is defined as, it is the ratio between energy stored by energy loss per oscillation cycle, energy loss per oscillation cycle, and it's multiplied by a factor of 2 pi. And in cavity optomechanics, we need a cavity with high quality factor, because higher is the quality factor, higher would be the number of oscillations of the photon inside the cavity. In fact, finesse also has the same meaning. Higher the finesse, higher would be the number of oscillation of the photon before it leaked away from the cavity. And we'll see shortly that quality factor Q and finesse are related. In fact, they are actually the same thing, but we'll see the relation between them very soon. Now, you know, if the survival probability of the photon inside the cavity is PS, then for an optical cavity, the fraction of energy that is lost per round trip, the fraction of energy lost per round trip is 1 minus PS. Okay, the rate at which energy leaves the cavity is the rate at which energy leaves the cavity is inverse of the photon lifetime, so 1 by Tp, because Tp is the photon lifetime and it is relative to the amount of energy that is stored in the cavity. We can understand it this way also, because you see that in terms of survival probability, the probability to survive n round trips in the cavity would be ps to the power n. For one round trip, survival probability is ps. For n round trip, it is ps to the power n. This we can write as ps to the power, this number of round trip would be time divided by one round trip time. This we can write in this form, e to the power t by trt, that is the round trip time, into logarithm of ps with base e. So this I will explain. This I can also write it as e to the power minus t by trt 1 minus ps. In fact, this I can write because I already know the expression for the lifetime of the photon, that is tau p. While writing it, I have used using this relation, that logarithm of 1 plus x. For very small x, I can write it simply as x. For small x, where I am taking x is equal to say 1 minus ps. So, and photon round trip, photon lifetime is round trip time divided by 1 minus ps. So using this, I see that the energy loss is exponential in time. So, and it has a loss rate is 1 by Tp. So this way also we see that energy loss rate is 1 by tau p. Okay, so in fact the energy loss per oscillation cycle is just the optical period multiplied by this rate. So I can write that energy loss per oscillation cycle is equal to optical period multiplied by energy loss rate, and optical period is in terms of frequency. I can write it as 1 by nu m, that is the resonance frequency of the cavity, and this loss rate is 1 by tau p. So you can, with respect to the stored energy, so therefore the quality factor, as you can see, it would be 2 pi into we have simply nu m tau p. So this is the expression for the quality factor. Now, due to this relation that we had earlier, the uncertainty relation, that tau p into delta nu full width at half maximum is equal to 1 by 2 pi. So clearly we can write that quality factor is equal to the resonance frequency divided by the full width at half maximum. Okay, so this is what we have. By the way, if we compare with the expression for the finesse, which was defined as free spectral range divided by delta nu at full width at half maximum, this is the bandwidth. And if I compare this relationship, and also you note the fact that this resonance frequency is basically integer into c by 2l, which is nothing but the free spectral range. So immediately we get a relation between the quality factor and the finesse, that would be Q is equal to integral multiple of this finesse. So both of them are basically essentially gives us the idea whether it is quality factor or finesse. It essentially gives us the idea about the number of oscillation a photon or light makes inside the cavity. We have now learned enough about Fabry-Perot cavity. Let us now go back to our cavity optomechanical setup. In the cavity optomechanical setup, we have one mirror fixed and the other mirror is movable. Let us say the other mirror is attached to some spring. This mirror is fixed and this mirror is movable. And as you can see, if this mirror is not movable, then this is the typical Fabry-Perot cavity, and the length between these two mirrors is say L, while this particular mirror is also fixed, but it can of course displace by some amount say X. And this is the typical cavity optomechanical setup, or I can just say cavity optomechanical system. This is a prototype. One of the mirror, say this one is or this one, let us say this one is fully reflecting. Say this is fully reflecting, and this particular mirror is partially reflecting, or transmitting, so that light can enter into the cavity. As you will see later, that this displacement X of the movable mirror turns out to be a very important variable. Now let us guess the Hamiltonian. So now we'll do the guessing work, and later on we'll of course study this Hamiltonian in great details. Let us now guess the Hamiltonian, which is not very difficult because you know that the total Hamiltonian of the system, let us say it's say H, is due to contribution of various parts. Let us say one contribution is going to come from the optical photon inside the cavity. So say optical photon inside the cavity. The other contribution may be from phonon in the mechanical oscillator, which is the movable mirror. So this is due to the phonon, and there would be interaction between the photon and the phonon. So this is photon interaction term would be there. This would be photon, a Hamiltonian corresponding to photon interaction. Apart from that, this cavity we have to throw a laser light, so or that means we have to drive the cavity by laser light. So therefore there will be a term which should be in the Hamiltonian, total Hamiltonian, and that would represent the laser drive. And not only that, we'll have dissipation of this photon will eventually decay from the cavity, or even the phonons in the mechanical oscillator will also decay. So there will be a Hamiltonian a term which will be responsible for all dissipative processes. So let us say that is H dissipation. So these are the contributions that we'll have. Now let me explain these terms one by one in a little bit. Of course, we need to know to one thing, that this optical cavity contains infinity of normal modes of electromagnetic field. However, this laser light that is getting incident on the system would have a fixed frequency. We'll have some fixed frequency, and it will be only that light will be able to enter into the cavity which will be close to one of the optical modes. As you know that this cavity is going to support many modes, because we already see that nu is equal to for Fabry-Pérot cavity it is integral multiple of c by 2l. So therefore many modes are possible, but we'll consider only that particular mode which will be close to the laser frequency, incident laser frequency. Okay, so we'll focus only on a particular optical mode. Now the optical mode, as we know, is a harmonic oscillator, so we can write that for the optical mode or the cavity mode, Hc is equal to the energy. This is the harmonic oscillator energy. Say optical frequency is angular frequency is omega opt, and this is going to be a function of this displacement. I will explain that. This is the energy of a optical photon, and that will be the number of photons having the same frequency. So this is the Hamiltonian, but optical mode frequency, now here this quantity depends on the displacement of the mirror. If the cavity has fixed length, then we know that this resonance condition, that would be some integral multiple, let us say now integer is n into pi c by l. Okay, this is omega, not nu. So this is the resonance condition for a cavity with fixed length. Now due to the small displacement of this in mirror, this movable mirror, I can write omega opt, this is a function of x. Now I can write it as n pi c divided by l. There is a small displacement, so I can write it like this. If I expand it, because x is very small, I can write this quantity in this way: n pi by l into 1 plus x by l. Okay, now this quantity is very small compared to 1, so therefore I can write it as n pi c by l. I can expand it as 1 minus x by l, and this quantity is nothing but the omega optical when with the fixed length, and the whole thing, then I can write it as 1 minus x by l. So this will enable us to write this Hamiltonian for the cavity photon, that is Hc is equal to h cross omega opt 1 minus x by l a dagger a, and this I can further write in, divide it into two parts. One, I can write it as the optical photon HO, and another one would be the interaction between the optical photon and the mechanical oscillator, which is actually here in the quantity x, right? X is coming from the movable mirror or the mechanical oscillator. So this particular term would be responsible for the photon-phonon interaction. So in fact, HO is, as you can see, you can read it from here, that from this expression it would be h cross omega opt a dagger a, and the interaction term would be minus h cross omega opt by l into x a dagger a. Okay, so these are important quantities. It is easy to see that the radiation process. What about the radiation pressure force? So the radiation pressure force, it's easy to see that the radiation pressure force would be h cross omega of A dagger A divided by L. Okay, let me explain it. Earlier we got this expression that the force is basically rate of change of momentum, and if there are n number of photons are getting incident, and for each photon the change in momentum after it is getting reflected from the mirror is say delta p, and this is the time. Now what we have here, n photon, the number of photon is A dagger A, and delta p is twice s cross k, which I can write it as twice s cross omega optical, the resonance frequency divided by c, and this time t. But this t is basically the round trip time, and t is equal to, let's say, 2l by c. Okay, and therefore because x is very small, so I can take the round trip time to be like this. So therefore the force expression, if I put this here, then immediately you will see that we are going to get this expression h cross omega t omega opt A dagger A divided by L. So this is the radiation pressure force. Okay, now this particular term, the interaction term, can be written a little bit in a different way, in a more familiar form actually. That would be h cross omega optical by L x A dagger A. This I can write as, because you see this is x is the displacement of the movable mirror. So this quantity we can write, because I have already used this A and A dagger. So for the this is associated with the mechanical oscillator. So let us say the annihilation operator, these things we discussed. So we can write it as B plus B dagger multiplied by the so-called 0-point fluctuation. So if I use this expression here, then what I can do, I can write it as minus h cross omega optical by L, and here I write x 0-point fluctuation B plus B dagger, and we'll have A dagger A. This whole thing, because this particular quantity, this has the dimension of frequency, I can write it as minus, or in fact rather I will write it this way. I will write it as h cross capital Z B plus B dagger A dagger A, where I am taking this capital Z as minus omega optical by L x 0-point fluctuation. Okay, so this Z is called the optomechanical coupling coefficient. So this is called optomechanical coupling coefficient. So therefore what I have this optomechanical interaction term. I can simply write it as h cross Z B plus B dagger into A dagger A. So this is a very important term, important component of the total Hamiltonian we have got. And just recall that this x 0-point fluctuation, this is h cross divided by twice m omega. Okay, m is the mass of the mechanical oscillator, and this is typically around, say, femtometer, 10 to the power minus 15 meter. And there are other terms in the total Hamiltonian. For example, this one, the mechanical the component due to the mechanical oscillator, and mechanical oscillator is also a harmonic oscillator. So here this capital omega here is the oscillation frequency of the mechanical oscillator. So here Hm would be, it's a harmonic oscillator, this would be H cross omega B dagger B. B dagger B is the number of phonons. Apart from that, we have this dissipation terms, and we'll talk about this later in the course in some more details. These terms has contribution from, first of all, the photons inside the cavity, coupled to the outside world from the partially reflecting mirror, and eventually it decays, photon decays at a rate kappa. So this photon decay rate is a kappa. Again, the phonons also decay. This is photon decay. This is photon decay contribution would be there in the Hamiltonian, and phonons also decay, and that is generally this decay rate is given by gamma, that is for phonon. Okay. Phonon actually decay because the cantilever or the mechanical oscillator, which is generally attached to some kind of a substrate, so the vibration of the beam may be transferred to the substrate. In a way, phonons leak out of the localized vibrational mode and radiated away to the substrate. This process is actually called mechanical damping, and the rate of mechanical damping is denoted by gamma. I can put a m here to emphasize that I'm talking about the decay of the mechanical or mechanical phonons or quanta of mechanical oscillator. Okay. There is however a one important difference between photon and phonons is there, because typically photons have a frequency in the range of photons have frequency of oscillation in the range of 10 to the power 15 hertz, and so the reservoir to which they are getting coupled effectively are considered to be at zero temperature because the oscillation frequency is so high. On the other hand, phonons oscillates, which we discussed or I said earlier, phonons oscillate in the frequency regime, say megahertz to say gigahertz, 10 to the power 9 hertz or 10 to the power 6 hertz. So there are always some kind of thermal phonons around, and it is quite possible that sometime thermal phonons will enter into the cantilever from the outside as well. So apart from that, as I said, there is the laser drive is also there, and we'll also talk about it later. So overall, to conclude, therefore we have the total Hamiltonian. We'll have these terms. One would be h cross, I can write it this way. Total Hamiltonian is h cross omega opt 1 minus x by L A dagger A. Okay, and then we have h cross omega B dagger B, that is due to the mechanical oscillator. Then we have this laser drive, and then we have all kinds of dissipation processes, or rather let me write it in this way also, h cross omega optical A dagger A, that is due to the photon inside the cavity. Then I have this photon interaction term, that is h cross Z B plus B dagger A dagger A, and this is from the mechanical oscillator. And then we have this laser drive, and then dissipation. Okay, so we have actually guessed what is the Hamiltonian of this cavity optomechanical system. Now we are going to discuss the basic physics of optomechanics in a qualitative manner. Let us consider this cavity optomechanical setup as shown in this diagram. Here this left hand mirror is fixed and the right hand mirror is attached to a mechanical oscillator, or it's a cantilever. So this mirror is movable. Now if this mirror is not moving, then say the length of this cavity is L, and in that case, as we know from our lesson on Fabry-Perot cavity, that light can enter, this laser light will be able to enter into the cavity provided this resonance condition is satisfied, where omega c is equal to n into pi c by L. Okay, however, because this right hand mirror is movable, this length changes from L to say L plus X, and accordingly this resonance condition is also getting changed, and resonance frequency would be n into pi c by L plus X. Now if X is a variable quantity, then the resonance frequency is also getting changed with distance. Now in fact, if we plot the resonance frequency versus this variable X, the plot will look like this. For a given mode, it will simply look like this. Okay, let me draw it by a different color. So it will look like this. In fact, there is not one resonance, there are multiple resonances in such a cavity, and because if I take various n, and then if I plot all these resonance frequencies as a function of position, we will get something like this. For various modes or resonance frequencies, it will, for a given mode, the resonance frequency will decrease with the variable X like this, and of course all of them are equidistant, so don't, okay, this should be equidistant. And if a laser with fixed frequency is incident, then we will have various positions of the mirror. Suppose the laser frequency is somewhere here, so this is fixed laser frequency. Then we will have various positions of the mirror. This is one position, this is another position, this is another position, like this. Okay, where the laser frequency will satisfy the resonance condition. This means that the light power or the light intensity circulating inside the cavity as a function of position will show a typical resonance behavior of Fabry-Perot cavity. So if I plot say light intensity or light power, light intensity or light power in the y-axis, and here this is the displacement of the mirror, then we are going to have various resonance peak separated equidistantly like this. So various peaks we are going to obtain. It has very sharp spikes when the resonance condition is satisfied. Okay, now we know that the light power is actually proportional to the radiation pressure force. So clearly this diagram is also a diagram of force versus position. So rather than light intensity or power, we can simply say that this is actually the radiation pressure force. Okay, so say let me write radiation pressure as F radian, radiation pressure force. One thing it immediately implies is that we have a strong behavior of force at the resonance positions. The force is very high. Another thing you can notice that this from this diagram is that at any given point the force has a certain slope. For example, if let us look at this particular point, say this point, okay, this point, you see that if I draw a tangent, you see the force has a slope here. That means we have a finite del f del x. That's the gradient, force gradient. So what does it mean? We know that in this case here, as you see, the force is position dependent. Then and also it is clear from this diagram that the force is position dependent. Then the slope gives an effective spring constant, say k is equal to minus del f del x. So the force gradient with a minus sign will give us the spring constant. Now as the mirror is moving towards right, we have a force pointing to the left. So you see the force is pointing to the left, and this force linearly increases in amplitude as we move the position. So this is exactly the effect of a mechanical spring. Now the overall spring constant of the mechanical mirror is increased due to the radiation pressure force, as the mechanical spring already has an intrinsic spring constant, and this effect is known as optical spring effect. This is called optical spring effect. Now this particular spring constant that we are getting, in fact the total spring constant of the mechanical oscillator would be due to the intrinsic spring constant, and this is because of the radiation pressure force, spring constant due to the radiation pressure force. So we are going to have an effective spring constant, and that will come due to the contribution from the one is the intrinsic one and another one is due to the radiation pressure force. And in fact this effect can be very strong, and sometimes it may be so strong that it may this increase in the spring constant maybe even exceed this intrinsic spring constant of the oscillator or the mirror. However, as you see that if the mirror is at another position, for example say this is at this position, so at this position, then we have zero spring constant due to the radiation pressure force, or we can even have reduced spring constant. Suppose here our position of the mirror is here, then as you see the slope is positive. Now if the slope is positive, the spring constant would be negative, right? And on the other hand, at this position the spring constant, the slope is negative, so therefore the spring constant would be positive. So let us say this is my position A, this is my position B, this is my position C of the mirror. At the position A, the effective spring constant of the mirror would increase. At position B, it will remain the same because contribution from the radiation pressure force would be zero. On the other hand, at the position C of the mirror, the effective spring constant will decrease. In fact, we can understand the optical spring effect from another perspective as well. So let us understand that. We know that is basically from the concept of potential. We know that the force is gradient of potential, that is minus dV dx. That is how we know if for a position dependent force, and force is negative gradient of the potential. So if we are given the force, then we can easily obtain the potential just by doing the integration. Then we can obtain, in our present case, a type of potential versus position curve. Let me first draw it and then I will explain. In fact, this is, I'm talking about the radiation pressure, radiation potential. So potential due to the radiation pressure force, and if I plot radiation pressure force versus position, we are going to get a plot like this. It will be kind of a staircase kind of a potential we are going to get. So whenever there is a resonance peak, for example here, as you see, whenever, as you can see, when there is no force, the potential would be constant, but when there is a strong force, the, or at the resonance, the force would be very strong, and we'll have a this this stair would be there. Okay, and we'll have another step, and again we'll have another step, and so on. Whenever we are having a resonance, we are going to have this step here. Okay, so these steps are actually rounded as the peaks are not infinitely sharp. This is only radiation induced potential. We need to, if we want to know the total potential of the mechanical oscillator or the movable mirror or the mechanical oscillator here, then we need to add the intrinsic potential that describe the motion of the mechanical object. And you know the mechanical oscillator oscillates simple harmonically, so therefore we'll have a parabolic potential like this. So the intrinsic potential would be a parabola like this. So consider it as a parabola. So this is our intrinsic, and on top of it I have to add the this staircase potential. Then I will have the full potential, then full potential versus position of the mirror or the variable x we can plot, and that plot will look something like that. If I add this intrinsic potential as well, then the plot will look like somewhat like this. Okay, so what is the significance of this resultant potential? If you look at it, then you will observe that there are several local minima here. For example, you can have a, you have a minima here, you have a minima here, you have a minima here, and so on. You can have a minima here. Okay, there are several minima. So this means that we have several equilibrium positions. The mechanical object can be at either one of these positions and is completely stable. In these positions, the radiation pressure force exactly balances the restoring force brought about by the intrinsic spring constant. Because you know, for a mechanical oscillator, a harmonic oscillator, the force, restoring force is minus k, say this is intrinsic, into x. So this relation, you know, this is directly proportional to the displacement. So this will balance out the radiation pressure force. So having this multiple stable position is known as multi-stability. This is called multi-stability. A typical plot of restoring force in a cavity optomechanical system, say the restoring force is, say this is my position, restoring force is directly proportional to position. So you will have this is the restoring force, and the radiation pressure force would be like this. Okay, so as you see, there are 3 points. Say this is one point A and another point B and this point C. Okay, this is due to the radiation pressure force. At this position, the radiation pressure force balances the restoring forces. So at point A, B and C, restoring force and radiation pressure force are equal. However, out of all these 3 points, only A and C, the point A and C are stable and B is unstable. Why? Because the rate of growth of the restoring force at point A and point C is faster than that of the radiation pressure force. Okay, so this is the phenomena of bistability. So there are 2 points at which this cavity optomechanical system would be stable. Okay, so this is the phenomena of bistability. It's called bistability. Please note that optomechanical spring effect is already experimentally demonstrated way back by a group of Harvard weather group. In 1980s, they experimentally demonstrated this effect. Let me stop here for today. In this lecture, we tried to understand the basic physics of a cavity optomechanical system, assuming that the light reacts instantaneously to the position of the movable mirror. That is, when the mirror moves very, very slowly. In the next lecture, we'll examine the dynamical case, and then we'll start discussing cavity optomechanical system quantitatively, first by examining the classical regime. So see you in the next class. Thank you.